This girl's flight to space? Well, that involves calculus, and I'm here to show you how. Here we have a simple first-person video game with a scene that you might find in an open-world environment. Most modern video games with many hours of content now have very high standards for physics engines, and look much better than this. Even something simple like a puzzle game might have a particle effect that falls down the screen, accelerating as it does to simulate gravity. For more complicated examples, such as a first-person shooter, there's a lot more involved. The reason for this standard is obvious. For things to be realistic, they must imitate the modern world. If I throw a block upward, I expect it to fly up and then back down. Of course, I can add a gimmick to say that gravity has been flipped, and that'd be fine. Oh, well, not really. In Unity, collisions are handled for us, so we don't have to write any code for what to do when two blocks collide. However, there can be many collisions that take place in a single frame. And I mean many. In Unity, each object is called a game object, and each game object can have components attached to them. A component called a rigid body is attached to each game object in the simulation. So every block, sphere, and capsule you see as a rigid body, it has the rigid body component. This allows the game object to be affected by forces. For example, the gravitational force, a magnetic force, or collisions, like this big unrealistic looking cannon sticking out of my arm. As we are in 3 dimensions, as you can see, there are I hat, j hat, and k hat vectors representing motion in each dimension. So you can think of them as x, y, and z. If you look in the top left corner of the screen, if I select an object with my crosshair, I will see its position, velocity, and acceleration, and a bunch of other information. I'm calculating the acceleration simply by taking the difference between the velocity of the previous frame and the current frame, divided by the time step between the 2 frames. So that's just the same as the formula for constant acceleration. The time.fixed delta time is the time elapsed between 2 measurements of velocity. So why are collisions so important in a video game? Well, not having proper collision detection can be a game-breaking bug. Oh, yeah, like that. Oh, shh. Now, collisions would theoretically be calculated with a formula like the one shown on screen. Essentially, for each dimension, I, j, and k, or x, y, and z, we calculate the force applied to an object over a period of time. This gives us an impulse vector, or effectively a change in velocity. This also applies to angular impulse, a change in the speed of rotation. If 2 blocks collide mid-flight, you'd expect them not to bounce off without rotating. These equations, however, are impractical for computers because they don't know what an integral is. You have to tell them. Computers use precise estimations instead and calculate the position and velocity of an object each frame to simulate forces. These methods include Euler's method, which we are familiar with, the Verlay method, and the Runge-Kutta method. Euler's method takes one approximation at some time interval, let's say frame 0, and predicts what the velocity and position will be sometime later at frame 1, let's say. This method, although very simple to implement, can be prone to error, especially when dealing with large changes in velocity in small amounts of time. So sometimes the 4th order Runge-Kutta method is used, which has the same principles as Euler's method, but with a weighted average of multiple slopes taken across the given time step. Euler's method can be essentially thought of as a 1st order Runge-Kutta method. Without getting into too much detail, this method is generally more accurate, but harder to implement. The Verlay method is different because it calculates a change in position as if it were using simple kinematic equations, each of which is calculated from the previous and next time step. The simplest way to show why the Verlay method is effective is that it only requires us to know our previous position, current position, and the acceleration. The actual math is done with a Taylor expansion of the position function x of t plus or minus delta t at some current time t sub n. This then can be applied to each dimension. This first equation up here just describes one-dimensional motion of an object moving. So initial, velocity, acceleration, and jerk. Then we write a Taylor expansion, so we need to first find the derivatives of x with respect to time t. So we have x, dx dt, dv dt, and then dA dt to get our three first derivatives. Then finally we use the formula for our Taylor expansion. And then we write one for both x at t plus delta t and x at t minus delta t. Then we can just add them together, which gives us our equation for Verlay integration. And of course, we have our error term at the end. So as you can see in this final equation, this 2x at our current time, t sub n, is our current position, which we can measure in game. The x at t minus delta t is our position one time step ago. So let's say the previous frame, which can also be obtained through measurement. And then the a t sub n term is our acceleration, which can be given or calculated. So that's pretty easy. So how is this useful? Well, the integration of, for example, acceleration that would have been impossible only given certain vectors, like the vector of position and velocity, is now possible because the integration happens like a Riemann sum. Every frame and iteration of this equation is calculated, and eventually the precision becomes indistinguishable from an actually exact value. And of course, all of these methods can be turned into their angular equivalents and can be applied in each of the three dimensions. Let's say you want an enemy character to follow behind a player and then attack them when they're close enough. Just following the player won't be enough because there's going to be obstacles in their path, like this brick wall right here. We can define an obstacle as any object in a game that impedes the movement of an object with behavior, so the player or the enemy. So we must write code that allows the enemy to find a path to the player given set conditions. Unity has a built-in pathfinding feature that we can use, and using set parameters, Unity can build a navigation mesh, or a nav mesh, which calculates the surfaces that some given character can run on. From there, Unity can determine the shortest path between 2 points. One way of calculating the shortest path is known as the A-star pathfinding algorithm. This algorithm essentially searches each movable location on a predetermined grid and assigns each square of the grid a score based on the sum of the distance from the origin, let's say function c, and the shortest path to the destination, we'll say s. Then the algorithm starts at the origin and moves to the cells where this sum is minimized. This algorithm does not involve calculus, but it's commonly used due to its simplicity and efficiency. I bring this algorithm up to focus on the idea of minimization, or finding the shortest path between 2 points. Archimedes said the shortest path between 2 points is a straight line, but what if I have an enemy spaceship being influenced by varying gravitational forces and futuristically strong electromagnets? The A-star pathfinding algorithm would quite literally get lost. We need to find some way to figure out the path of an object and optimize that path to get the fastest. Sure, we can just keep writing code until we get something that works, but calculus is cool, so I'm going to introduce Lagrangian mechanics. You see, Newtonian mechanics are easy to implement and use for most cases, but we have to constantly split forces into individual vectors, which can get complicated. So I'll pretend I know what I'm talking about by reading and learning from this 4-page paper, which is shown on the screen. Lagrangian mechanics deals with, well, Lagrangians. To start, we can define a Lagrangian. This will be a functional or a function of functions. So the most common one is the one shown on screen. So what are our two functions? Well, here it happens to be that of kinetic energy T as a function of the rate of change in position, and potential energy U as a function of position. And what function gives us kinetic energy? Well, that's 1/2 mv squared, the kinetic energy of an object. Now we can do some fancy partial derivatives. Seems scary because there's two variables and fancy symbols. Well, what if I told you that the partial derivative of L with respect to x just means that you treat every independent variable except for x as a constant? So the partial derivative of this whole thing with respect to x is just equal to 16x cubed. So now let's go back to our function. We'll first take the partial derivative of L with respect to v, or the rate of change in x with respect to time, and then with x. So what's the point of all this math? Well, that's where I'm getting to. The Euler-Lagrange equation is a second-order differential equation that can be used to minimize and maximize some given functional. Remember, our functional here is our Lagrangian. So the Euler-Lagrange equation is shown right here, and we'll show you how to derive it in a very simplified way. So we actually start from Newtonian mechanics. We do F equals ma. The Euler-Lagrange equation is actually kind of an analog to the Newtonian version of F equals ma. And we write this F equals ma as F is equal to the negative derivative of potential energy is equal to ma. So this negative derivative of potential energy just represents the idea that if you drop an object from some height h, gravity exerts a downward force on that object, but the object is losing gravitational potential energy, mgh, while gaining kinetic energy 1/2 mv squared, as if it were being pushed by gravity. And of course, force over distance is work, which is joules or energy, so the derivative of work with respect to displacement goes back to force. Then we can obtain this ma part by taking the derivative of mv with respect to time, because doing so turns velocity to the rate of change in velocity, or acceleration. So our final equation is here. Now we just plug in everything from before, and that's the very simplified way to derive the Euler-Lagrange equation. With this equation, we can find any Lagrangian relating potential and kinetic energies at some point. For example, if you have hundreds of gravitational forces, then you can just find the sum of potential gravitational energies at some point, and then find the kinetic energy of a given player with in-game stats. So now you can plug that into the Euler-Lagrange equation and then just solve. This method might only be used in some niche cases, so not every video game has to deal with the problem of gravitational forces or magnetic forces, but it's just one useful way that calculus can be integrated into the physics of a game. Well, here we have a video game with no lighting, and here we have a video game whose lighting is completely messed up. See how the sun provides less light than this measly floor lamp here, which just doesn't make sense. Let's fix that. Oh, that's not quite the sun, but it's close. One sec. Lighting is really tough, because doing something as simple as turning on a light bulb causes every object in the scene to change its appearance. You can, turn off the nearest light if you don't believe me. You can't call a game realistic without having accurate lighting. There's not much real calculus involved in lighting, but there is a lot of math involved. So, for example, dot products, cross products, and trigonometry. But it's still an interesting topic that I want to talk about. To start, I should talk about the general model for calculating what an object looks like under light. It's a pretty simple equation, actually. The illumination of an object equals ambient plus diffuse plus specular lighting. So do note that not all three components need to be present at once. I'll talk about how we get each of the components. So firstly, ambient light is kind of the default amount of light when no other sources are present. It's not very realistic, but it ensures that in very dark environments in video games, you are still able to faintly see objects and still able to play the game. Diffuse lighting is why we see objects at all. because light is reflected off of surfaces into our eyes in the real world. So specular lighting is what gives objects that shine. It makes the surface look kind of smooth. If we look at these two objects, pictures that I took, we have a lunchbox and a Darth Vader figurine. We can see both objects because of diffused reflection. However, the plastic part and the metal ring of the lunchbox and the figurine itself is shiny because of specular lighting. Lighting is done in a lot of different ways. Traditionally, lighting is done with a process called rasterization, where 3D objects are rendered in a 2D sheet of sorts. This process may have some downsides, but it is the most efficient and fastest method because groups of pixels can be, grouped into polygons, so the amount of calculations that have to be performed is much fewer. For example, we take the Phong reflection model, which is shown on screen. It seems complicated, but it's literally just the same image that I showed before. The first part deals with ambient lighting. That's simple because it's the same for everything. Remember, this is what you can see when everything's dark. The rest is a summation, which factors in all light sources, hence the summation, and it says that each light source causes a diffuse and specular illumination on a given object. I won't get into the exact math, but each pixel or polygon will have this calculation run, and they add up into one whole surface. In Unity, something called Lambertian Reflectance is used when dealing with a matte or non-reflective material. As shown here, this wood is matte, and its appearance does not change based on what angle I look at it. However, the starting surface here on top looks almost like a mirror. It's very reflective, and you can see how the reflection changes as my viewing angle changes. These reflections use the Phong reflection model, which is only different because of the vectors it uses to calculate specular lighting. As you can see, there is quite a lot of math involved in lighting.